Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to tell you about a very important concept in algebraic geometry, which is the notion of a Weil divisor. And that's the notion that allows you to talk about the location and the order of poles and zeros. Okay, so let's see what the setup that we have is. Suppose X now is some quasi-projective irreducible variety. Okay, so recall the notion of a prime divisor firstly. So that just means a irreducible closed subvariety of X, say D, which is of codimension 1. So that basic idea here is that if you have a function on X, right, if you look at the location of the zeros or the poles, that should carve out something that is one codimensional. Okay, so let's look at the definition now of what a Weil divisor is. So what we're going to do is we're going to look firstly at the free abelian group generated by all these prime divisors. And that's going to be denoted div X. So what do I mean by free abelian group? This is just the set of all formal Z linear combinations of these prime divisors. Okay, and since it's a formal Z linear combination, you can add two of these elements together, so it forms an abelian group, and it's the free abelian group. And the elements of this free abelian groups, they're the Weil divisors. Okay, so that's easy enough. So the other thing that's kind of useful is that on this set, you can talk about a so-called positive cone, okay, and put a partial order on it. So what are those positive elements? So we say a D, an element of this group here, is effective if it's actually some n linear combination of prime divisors, okay, and in that case we write D is greater than or equal to 0. So fairly natural definitions here. If it looks a little bit abstract, maybe we'll keep to a very, very simple sort of a case. If we look at a curve X here, then what are the prime divisors? Okay, so you're looking at codimension 1, which is just as mentioned 0. So you're just looking at points, okay? So each of the points give you a prime divisor. That's what a prime divisor is, just the points here. So this group here is div X is just the set of all formal Z linear combinations of points, like you see here. So N1, P1 plus all the way down to NR, PR for some finite R here. So the N's here are just any integers, and the PI's here are just some points. And that's a notion of a divisor on a curve. Okay, and as I said, the reason why we're interested in this sort of thing is to look at poles and zeros of functions, rational functions. And to do that properly, we'll need to assert some extra conditions on this projective variety or quasi-projective variety X. We want it to be normal, okay? So suppose we have a normal variety X now, and that its field of rational functions is K of X here, okay? So what we're going to do is, if this is non-zero, so we have F here is some element which is non-zero rational function, I want to assign to it some sort of a divisor. So I want to basically say for each prime divisor, I just need to give you the coefficient of that prime divisor, okay? So we'll fix a prime divisor D, okay? And remember that if we have a prime divisor D on a normal variety, then you look at the local ring at the generic point of D, okay? So that's OXD. And this is going to be a discrete valuation ring, because it is normal, being a localization of a normal variety. Okay, so that's going to give you this, discrete valuation ring. And in particular, being a discrete valuation ring means that it has a unique maximal ideal, and that's prime and principal generated by, say, some element. Let's call that element pi d. So this is not unique, but it's unique up to a unit, and it's called the uniformizer pi d. Okay, and that's the thing that we're going to use to determine the value of a pole and zero. So essentially, you should think of this uniformizer pi d as some function which has a zero of order 1 along d. Okay, that's kind of how you should think of it. Okay. So now remember, you have this valuation map, okay, from kx cross, which is also the function field of this local ring. Okay, it's the fraction field rather of this local ring. To Z. And what does it do here? So basically what you can do is you take this element F inside here. You can look at the OXD module generated by that F, okay? And since this is a principal ideal domain, okay, and a DVR furthermore, you know that this has to have the form OXD times some power of this pi d. Okay, so all ideals have this form here, and even all the fractional ideals, okay? So this N here, this index here is going to be the end that you assign here, and that is basically the order of the 0 along D. And you can do this for every prime divisor D, and that's going to give us the next proposition, which actually defines for you how to record the zeros and poles of a function. Okay, so we have a well-defined group homomorphism from the kx cross. This is the multiplicative group of non-zero rational functions on x to this group of Weil divisors on x, div x. Okay, and it's very simple what the definition is. Okay, so what we do is for each prime divisor D, we apply this valuation map nu d of f. That gives you basically the order of the 0 of f along D, and that's going to be the coefficient of D, and you need to make that sum. And the nice thing is that this is actually a group homomorphism, and it's well defined. Okay, so let's just say some words about this. So the first bit to notice is that why do we need to check that it's well defined? I guess the thing that we need to check here is that most of the time this nu df is equal to 0, so there are only actually a finite number of summands here. Okay, so that's what we need to check. Okay, so what does it mean to be 0 here? Okay, nu df to be 0. So that means that the function is neither a 0 nor a pole along that D. Okay, and the key point is that if you look at this f, right, it's going to be well-defined non-zero on an open set, and x being irreducible means that that's a dense open set. So you can look at the complement of some dense open set, so you'll get some closed subvariety. And since you have a quasi-projective variety here, that has to be a union of a finite number of the divisors. Okay, so there are only a finite number of places where those poles and zeros can be. Okay, so that's the reason why it's well defined. The other thing you need to check is that it's group homomorphism. So that means that if you have to check this, I guess you need to check that it takes products to sums. The sums here is coefficient wise, so you just need to check that in fact each of these nu d's are group homomorphisms. So let's just do that quickly now. Okay, so let's see where fg, nu d of fg, okay, let's compute this left hand side here. So what do? We look at fg times this oxd. That's what this recipe tells us here, and we have to say that's the same as the principal ideal generated by what power of the uniformizer. Well, f oxd, that's nu df says that that's equal to pi d to the nu df oxd. Okay, by definition of what is nu df, and this also is some generated by some power of pi d. Which one? It's the one that's generated by nu dg, power of pi d. Okay, and so you can see that when you multiply these together, this is just a principal ideal generated by pi d to the nu df plus nu dg. Okay, so that means that what this value is here is just nu df plus nu dg, and that shows that this is indeed a group homomorphism. So that's rather nice. If it's a little bit abstract, I think hopefully if you look at this following very simple example, all these concepts will be very clear. Okay, so let's have a look at the projective line P1 with homogeneous coordinates x and y. So you can write this as the union of the affine line with coordinate z, where z is y on x, with the affine line with coordinate z inverse. And let's pick a non-zero function. Let's pick z times z minus 1. So this is a rational function on P1, and so is this polynomial in z. Okay, so let's have a look at this. Of course, you can think of this as a function that is defined on this A1z. So certainly it's you can look there first, okay, and you'll find that there are no poles there, but it's got zeros at z equals 0 and z equals 1. Z equals 0 is the point 1 colon 0, and z equals 1 is the point 1 colon 1. The only pole that it will have is at infinity. Okay, so we need to also investigate infinity. So the only zeros and poles are at z equals infinity, which is 0 colon 1. Okay, so this is an example of the fact that this is a well-defined group homomorphism. Okay, there are only a finite number of points here, right, where this rational function here can have poles or zeros. Everywhere else, okay, is going to be a non-zero, okay, and it's going to be well-defined. So being well-defined means it lies in the local ring, okay, it lies in the local ring, and because it's non-zero, that means it's not in the maximal ideal, okay. So that means that it's actually going to be an invertible element, and also it means that the value or the valuation map is going to give you a 0. Okay, so we just have to check out these 3 points. Okay, so at z equals 0, of course, the order of the 0 here, this is z times z minus 1. Okay, so I guess you just need to look at the order of the 0, z minus 1 at 0 is, of course, 0, and the order of the 0 here is 1, so that's just 1 here. Similarly, the order of the 0 at 1 is just 1. The order of the 0 pole at infinity is more interesting. So what we do is we have to work in the local ring at infinity. And there, what's the uniformizer? The uniformizer there is Z inverse. Okay, so basically, where is infinity? It's where Z inverse equals 0. So Z inverse is the uniformizer there. Okay, so we're going to write everything in terms of a Z inverse. So firstly, I'll pull out factor of Z squared from here. If I pull out Z squared, the first time I'll get a 1. From the Z here, minus Z, I'll get a minus Z inverse. So this part is written in terms of Z inverse. So I need to write this in terms of Z inverse as well. So this is Z inverse to the minus 2 times 1 minus Z inverse. Okay. So if you look at this, so what is the, so this is going to be a unit, okay, at infinity. And here, what's the power of Z inverse that you need? Minus 2. Okay. So when you evaluate this new here, you get minus 2. In other words, there's a pole of order 2 at infinity. And hopefully you can see where this comes from. It comes from the fact that this is a quadratic polynomial in Z. Okay, so at infinity, it will have a double pole. And now you can form this, the divisor that's associated to this function. Okay, the divisor is, well, the value at 1, 0, the coefficient here is just 1. So you just have one of them. At 1, 1, you have a coefficient of 1. And at 0, 1, you have a coefficient of minus 2. So you subtract 2 of them. So this is the divisor associated to this function here. It's just 1 colon 0 plus 1 colon 1 minus twice 0 colon 1. Okay, and it records a lot of information about this function here. Okay, it tells you how to a single pole, a double pole at infinity, a single 0 at 0, and a single 0 at 1, and no other poles or zeros. And the thing about this is that if you just look at this, how many functions have this this divisor associated to them? In other words, a single 0 at 0, single 0 at 1, and a double pole at infinity. Well, the only thing that you can have is just scalar multiples of this. Okay, scalar multiples where you multiply by some scalar inside your field. Okay, so this really captures a lot of information about your function, and that's one of the reasons why in algebraic geometry this is such an important notion. Okay, up to constants, this is going to retain you everything that you know about this function. Okay, and that function is recorded in terms of important geometric data associated to that function. The last example suggests that the divisor tells you a lot of information about rational functions. And so what I want to do here is to show you in general what the situation is. How much information does this divisor actually retain? And to do that, we'll need the following theorem, which unfortunately I can't give you the proof of, but at least I can tell you the reason why it ought to be true. Okay, so this is something that perhaps is intuitively ought to be true on geometric grounds. Suppose now that x is a smooth variety, although this actual result is going to hold even for normal varieties, although the proof will be quite different. In this case here, for this divisor f to be effective, this occurs if and only if f is regular. Okay, so if f is regular, of course, it has no poles. Okay, so when you work out this divisor, there are no negative coefficients that occur. They're all non-negative, so that's why the divisor is effective. But what I want to say is that this is actually also necessary and sufficient criterion for effectivity. Okay, so let's suppose now we have this holding and we want to show that f is actually regular. Okay, so we'll do this by the contrapositive. Okay, so suppose f is not regular. If it's not regular, it's not defined at some point p. And the fact that we're going to use, how we're going to use smoothness here, the key thing here is that in the local ring OXP, it turns out that if it's smooth, it's actually a unique factorization domain. Okay, so this rational function f, okay, it's a rational function, so it certainly can be written as a fraction g over h of elements inside this local ring here. Okay, but since it's a unique factorization domain, you can talk about primes, okay, and you can talk about these being relatively prime. Okay, you can cancel, you know, prime elements until these g and this h are relatively prime. Okay, and so of course what you want to do for the contrapositive, we want to say if it's not regular, then you want to say that it's got poles somewhere. So where are the poles? The poles are precisely where the zeros of h are. Okay, so where there are zeros of h, okay, that will give you some divisors which don't cancel with divisors upstairs from g because these are relatively prime. Okay, and that gives you the reason why this at least is true in the case where x is smooth. The normal case requires a slightly different argument. And from that, now we can have a real analysis, okay, and understand when do two functions have the same divisor. Okay, so suppose f and g are non-zero rational functions. When do they have the same divisor? So in the previous example, we saw that in that very special case, it's when they differ by a constant. So in general, the result is that f and g, they differ, okay, by some unit in the global sections of this OX. If you're not so clear about what this is, I'll say a little bit more about when I explain why this is true. Okay, so they just differ by this unit here. Okay, and since this is a unit, that means that when you multiply by this unit, of course, it doesn't change OX. U times this OX is just going to be OX. Okay, so U is basically a global section of this OX. Okay, it's an element of this when you evaluate on all of X. Okay, so you can multiply anything by that U, and if you multiply OX by that U being a unit, means that you just get OX. So of course, that's equivalent to exactly this statement here: F times OX. Okay, so this is going to be a sheaf, and where does it sit? Because f sits inside kx, this sits inside the sheaf of the constant sheaf of this kx, so that's denoted by the script k very often. Okay, so if you look at these two subsheaves of this constant sheaf of rational functions, the script k, these two will be the same. So that's another way of writing this condition here. And it's very easy to see why this is true. Okay, but let me just state some more things. Okay, so why the last example works is basically because x is projective. As x is projective, it turns out that this is very, very small. Okay, this ring here is just the base field. Okay, all the non-zero elements in the base field. So if x is projective, actually, then this condition that they have the same divisors just means that f and g are the same up to scalar alpha inside k. And that's a really nice result. So that's really telling you that this basically captures almost all the information that you want about this function. Okay, just up to that scalar. So that's just up to a very small piece of information there. And the reason is it just more or less follows just from this theorem, which is rather nice. Okay, so what does the theorem tell us? Okay, so the way we'll use it is that, well, if you look at the divisor of f divided by g, let's call that u, f divided by g. So that gives you the u here. Okay, this is going to be a rational function at least. And you can say what are the divisors of this rational function, divisor of u. Okay, because the divisor, this here is a group homomorphism. It's the divisor of f minus the divisor of g. And since these are equal, that's equal to 0. And in particular, it's effective. So that tells us that this u, okay, this unit here, this rational function here is actually regular. Okay, it's actually a regular function. So it's a global section of OX. Okay, it's a regular function on all of x. Similarly, if you look at u inverse, what's u inverse? That's g on f. And the divisor of this u inverse is going to be the divisor of g minus divisor of f, which is again 0, and that's effective. Okay, there are no poles, so therefore it's going to be regular as well. So both u, this rational function u, and this rational function u inverse, they're both regular on the whole of x. So basically, there are no zeros, no poles. Okay, and it's going to be a unit. Okay, so that's why this u is. Of course, you can always write this for some rational function u, and the point is that u is actually a unit in here. Okay, so it's going to be a global section. Okay, a globally defined regular function, which is never 0. Okay, and this shows you how this this technology of looking at this divisor really tells you a lot and gives you a good way to study rational functions in algebraic geometry. I hope you enjoyed this adventure in pure mathematics.